Alright, welcome to our second physics video, 1.2 Uncertainties and Errors. Now, uncertainties and errors are a very big part of physics because, well, physics is the study of how the world works, and to learn about how the world works, we need to take measurements about the stuff around us, observations and such. That involves uncertainty. No matter how precise, how accurate, how wonderful your instrument is, you'll always have uncertainty. It's unescapable. It's this monster that just follows you around wherever you go. Even if you're using an electron microscope or the Large Hadron Collider, there's still uncertainty, which is why we need to learn how to measure it. Now, firstly, we need to figure out, how do we determine the validity of our measurements? And there are three main things that we use to determine that: accuracy, precision, and scale. Accuracy is how close your measurement is to the accepted measurements. Let's say we know that the atomic mass of carbon is 12.01. Well, let's say you took a measurement and you got 12.00. That's a very accurate measurement. It's very close to that accepted value that physicists and chemists and scientists have decided is the value for the atomic mass of carbon. Precision is slightly different. It's how close all your measurements are to each other, regardless of the true value. So let's use carbon again. Let's say all your measurements, you got 10.00, 10.01, 10.00, and 10.02. Those are very precise measurements. They're all very close together. Your measuring tool is very precise. However, those are not accurate at all. It's nowhere near 12. It's 10. It's 2 less. It's a pretty large margin of error. So you can see there are some differences between accuracy and precision. Never equate them. That's not something you want to do. And then, of course, there's scale. How large is the scale of the item you're using? Of course, a ruler that goes 1, 2, 3, 4 is not as precise as, say, a long measuring tape that goes 1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Your scale depends on how much uncertainty it will create. It will give you the uncertainty that you're trying to find. If your scale is smaller, you'll have less uncertainty because you've got smaller measurements that you can make. Speaking of uncertainty, there are two major sources of it in the form of error. Now, the first one is systematic error. We're just going to kind of brush over that because your real uncertainties won't come from systematic error. Systematic error is when there's an issue in how your experiment is designed. So let's say that you're measuring how high a ball bounces when you drop it. Let's say you start your timer too late. That's some systematic error right there. The only way to fix systematic error is to fix your experimental design. So it's usually human error. We don't really take that into account when talking about uncertainties. The real thing here is random error. Random error will always be there. That's just the natural error you get from taking measurements, your natural uncertainties. And that can be reduced by taking multiple trials. The more measurements you have, the less random error you're likely to get because you can take means. And from your random error, we get uncertainties. Now, what are uncertainties, you may be asking? And uncertainties are simply the margin of error in a measurement. So, let's say that you're taking a measurement of something with a ruler. Here's the ruler's scale. You've got a 1, a 2, a 3, and then you got little half marks in between. Let's say your measurement lies about right here. So we're going to guess, and we're going to say that that measurement is about 1.55. Your uncertainty is going to be in the form of a plus minus, and then because your smallest measurement is 0.5, you take half of that, which would be 0.0025. And thusly, you have your uncertainty, and that simply says that this value could either be 0.0025 greater or less than that, because we're uncertain. Our tool the scale doesn't get quite small enough for us to take so accurate measurements as to know if it would exactly be this. And so, when it comes to having different values, you might add them together. How does that equate with uncertainties? Well, it's pretty simple. When you're adding two values, or subtracting two values even, you just add those uncertainties. Let's say you've got 1.00 plus or minus 0.01 and 2.05 plus or minus 0.5. And you add those two values together. Your uncertainty is just going to be plus or minus 0.51. Now let's say you're multiplying that 1.00 plus or minus 0.01 by the constant number 2. You just multiply your uncertainty by that constant as well. You'd end up with 2.00 plus or minus 0.02. It's pretty simple when it comes to propagating uncertainties with addition, subtraction, and constants. Moving on. To reduce error. Now, we talked about having uncertainties. Now, how do you reduce them? Uncertainties are tedious. We have to add them and subtract them and all sorts of stuff. We want to reduce. We want to get our measurements to be as accurate and precise as humanly possible. And so let's say you have a data set. Let's just put a graph of it right here. You have your data set with a pretty standard deviation here. That's what it looks like. How do you reduce the uncertainty in this data set? Well, first, you look at how spread out your measurements are. You look at where most of them are. Most of them are concentrated right there. And then you look, these ones are out here and these ones are out here. These ones that are farthest from your big concentration of measurements probably have a larger concentration of error than these. So you're going to want to use these measurements that are focused right here. Another way that you can reduce your error is by taking the mean. The mean is just the average of all your data. You add them all together and then you divide by the amount of data that you have. And so, let's say the mean's right about there. The mean is going to be the closest to your actual value. Taking the mean will actually reduce your uncertainty because you get to divide your uncertainty by 2. And, however, if you have a smaller data set, let's say you only took 4 measurements, the mean won't reduce your uncertainty by that much. And so ultimately, you only probably want to just take half of the data and use that as a substitute mean. And finally, another way is by using standard deviation. Now, what is standard deviation? I'm just going to assume that you don't know what that is, even though you might. And it's just simply how far your data set is from your mean. You can get that simple standard deviation, we'll use d as our variable for that, by taking the square root of the distance of your first term. That delta x1 simply means how far that first piece of data is from your mean, plus that delta x2, your second piece of data, how far that's from the mean, all the way on to plus however many pieces of data you have, over the amount of data you have minus 1. And that's how you find your standard deviation. And your standard deviation just gives you which values are the most accurate and which values are the least accurate. And those are ways that you can reduce your error within a data set. And you may have noticed that when I was talking about that, I used graphs. And we love graphs in physics. Graphs are how we determine the relations between everything. Literally everything. And so you're going to have to learn a bit about graphical relationships. And now the key graphical relationship that we use most of the time in physics is linear. A line. A nice straight line. Most relationships like this, the key relationships that we want to learn about, are linear. Like take, for example, your distance equals your speed multiplied by your time. That's a linear relationship. It comes in the form of y equals mx plus b. You might remember from math class, that's your standard linear formula. Now, we don't have a b here, which is good. It starts at the origin, but your m is your slope. That's the gradient of your curve, your rise over your run. And then we know that distance and time are related proportionally. We love proportions in physics. Having things related proportionally gives us a nice, even way to relate them. And so distance increases with time at the rate of speed. Now, if your relationship is nonlinear, that's not necessarily good in physics. We don't like having nonlinear relationships because that doesn't give us a simple proportion like a linear relationship would. Let's take, for example, the relationship between the area of a circle and its radius. Now, if you graph the relationship between the area of a circle and its radius, you should probably end up getting something like this. It's a bit of an exponential curve. And so having that doesn't give you a nice proportion. We can't really determine the proportion between the area and the radius. So, if you recall the formula for an area of a circle, it's area equals pi r squared. So if you square all your values for the radius, if you take the graph of the area over the radius squared, you'll end up getting a linear relationship, which is like what physicists like. We like having a linear relationship. Now we can relate proportionally the radius squared to the area and get a nice even ratio, which is pi. Pi is that. It increases by pi. That's the slope of that line. So, but now, I mean, we just assumed that because we know what the formula for the area of a circle is, but how would you do that if, let's say, you didn't know that it was increasing it by squared? What if it was a equals pi r cubed, or a equals pi r to the fourth? Now, a simple way that we can do that, it's kind of advanced math, but I'm sure you've been through Algebra 2, logarithms. And logarithms make this quite easy. Let's take, we know we have area. We're not sure what that ratio is. I'm going to mark it with a k. We know we have radius, and then we have our n up here. Our n is the exponent we're trying to find. Take the log of both sides. Log a equals log krn. Using log rules, we can now separate this into log a equals log k plus n log r. And if you'll notice, that is a linear relationship, with your log a being your y, your log r being your x, your n being your m, and your log k being your b. And so, if you were to graph that, you just find the slope of the line, and the slope of the line would end up being 2, giving you what to do to your radius. You square the radius to get that perfect linear relationship that physics know and love. And so, that's how you make pretty much most of your graphs linear. Moving on, we go into the uncertainty of those lines. You know that I've talked about linear lines that us physicists, we love so much, but how do we measure uncertainty in those? You know that we can measure uncertainty of points with uncertainty bars, but measuring the uncertainty of a line is a bit different. What you do is you use those uncertainty bars to measure the steepest possible gradient you can have, and then the lowest possible gradient you can have. And once you have those two values, you simply take the steepest minus the lowest over 2, and you'll have the uncertainty for your gradient. And so that's how you find the uncertainty when you have gradients. And that pretty much covers it for uncertainty involving graphs. However, we still got a little bit left to cover because you can do something with that absolute uncertainty. So far we've covered what I call the absolute uncertainty, what IB likes to call the absolute uncertainty, that 1.00 plus or minus 0.01. Right there, that 0.01 is an absolute number. It's an absolute uncertainty. But for some purposes, it's more useful to have a fractional or a percent uncertainty. So how do you find that, you may ask? And that's simply you take your absolute uncertainty over the value that you've measured, and that's your fractional uncertainty. You want to turn it into percent, you multiply by 100. Now what is this useful? It's useful when you're multiplying your values times each other. Let's say you take 1.00 times plus or minus 0.01, and then you multiply it by 2.00 plus or minus 0.01. What you're going to want to do is you want to convert those absolute uncertainties here into percent uncertainties using that formula. And then once you have them, you add them. I'll let you do that on your calculators. I'm not going to do that work. Plus, it's good practice. Practice makes perfect in physics. Another thing that you can use them for is exponents, our wonderful exponents. Let's say you have 1.00 plus or minus 0.01 to the power of 2. Oh no, what are you going to do? It's exponents. Well, you convert that absolute uncertainty into a percent uncertainty using the same formula, and then you multiply that percent uncertainty by that exponent. And that's how you will get your new uncertainty. But it will still be a percent. Keep that in mind. Once you multiply it by 2, it doesn't magically turn back to an absolute uncertainty. It's still a percent. So how do you convert percent uncertainties back into absolute? If you will, pause the video, try to figure it out for yourself, but I'll be writing it here on the board after you unpause. You've got your absolute uncertainty over your value times 100 is your formula for percent uncertainty. So we're just going to work around that. Let's take percent uncertainty over 100 equals your absolute over your value. And then your absolute equals percent over 100 times your value. Pretty simple. And that concludes our uncertainties and error episodes. I'll be seeing you next week so we can get back into the nitty-gritty of physics and talk about vectors and scalars.